Today we'll be discussing about Kohlrausch's law of independent migration of ions. According to this law, say if there is an electrolyte NaCl and if it breaks in water as Na plus aqueous plus Cl minus aqueous in presence of water, then total molar conductivity of NaCl will be equal to sum of the individual molar conductivity of its corresponding ions. This is capital lambda and this is symbol of small lambda. This value we give for infinite dilution, that means nearly zero concentration. That means too much of water is there, excess of water. So how will we write the Kohlrausch's law for say MgCl2? MgCl2 will break as Mg2 plus 2Cl minus aqueous in presence of excess of water, that means at infinite dilution, such that molar conductivity at infinite dilution of MgCl2 will be equal to small lambda m, that means molar conductivity of the individual ions Mg2 plus there are two chloride ions, so 2 multiplied by molar conductivity of Cl minus ion. So this can be stated as the molar conductivity of an electrolyte is the sum of the molar conductivities of its corresponding ions at infinite dilution. At infinite dilution. So this concept can be seen in page number 83 of NCERT book. Why I always give the reference of textbook is because I encourage students gathering first-hand knowledge by reading books themselves. Teachers can only demonstrate it once, but ultimately they have also learned from textbook only. So why not to gain first-hand knowledge from textbook itself? So I'm making it easy because listening to any topic and getting the notes made in front of your eyes can make it very easy for you to understand primarily. But if you are a good reader, then it will be even better for you to see page number 83 NCERT class 12's part 1 chemistry book. You will not require any printed notes or any other downloaded material if you have NCERT book. NCERT book is the best book of chemistry for class 12th and even beyond. It contains all the basic concepts in a highly compact manner, and all rudimentary concepts are there related to theory as well as numerical. However, you can refer to a few side books if you have completed the example questions and the exercise questions and you want to do some spade work or some drill by solving similar type of other questions. So that would be the purpose of side book. Otherwise, NCERT's textbook is sufficient for you to get maximum possible marks in exam and for competitions even. So we will try to solve some numerical based on this topic. In page number 84, there is a question in which we have to find out. The question is calculate capital lambda, that means molar conductivity at infinite dilution of CaCl2 and capital lambda, that means molar conductivity at infinite dilution for MgSO4 from the data given in table 3.4. This is another reason why I always give reference of textbooks, page number, NCERT. As a CBSE teacher, it is our responsibility to encourage NCERT book as well as give apt guidance. So table 3.4 is in page number 83. So we'll again refer to page number 83 and see table 3.4. It is given that molar conductivity of Mg2 plus small lambda, molar conductivity of Mg2 plus is equal to 106.0 Siemens centimeter square per mole, and molar conductivity of Ca2 plus is equal to 119.0 Siemens centimeter square per mole, and that of we will require for chloride. So for lambda m for Cl minus will be equal to, these all values I am writing from table 3.4 itself. So this value is 76.3 Siemens centimeter square per mole, and lambda m for SO4 2 minus is equal to 160 Siemens centimeter square per mole. So lambda m for CaCl2 will be lambda m for Ca plus 2 into lambda m for Cl minus. So we'll put the value and get the answer. Lambda m of Ca will be equal to 119, and this will be 2 into this value 76.3, and the unit will be same for all, Siemens centimeter square per mole. This value will come out to be 271.6 Siemens centimeter square per mole. Part 2 of the question is you have to find out lambda m for MgSO4. This will be lambda m for Mg2 plus lambda m for SO4 2 minus. This value will be equal to, as per the table, 106 plus 160, and unit will remain same, Siemens centimeter square per mole. This value will come out to be 266 Siemens centimeter square per mole. So this was question number 3.7 of page number 84. See question number 3.8 of page number 83. Page number 84. Question says that lambda m for NaCl is equal to 126.4 Siemens centimeter square per mole. Lambda m for HCl is equal to 425.9 Siemens centimeter square per mole, and lambda m for NaAC is equal to 91.0 Siemens centimeter square per mole. Here NaAC means CH3COO minus Na plus. This part is called as acetate ion, and this is Na plus. So since we write positive at first and negative at last, that is why sodium is written at first and then acetate is written after sodium. Same is the case with this also. So AC means CH3COO minus, acetate ion. This is given value. We have to find capital lambda m for HAC. What does HAC means? AC means CH3COO minus and HAC means plus. So HAC is nothing but CH3 COO minus H. That means acetic acid or ethanoic acid. So to manipulate this data in such a way that we get this value. So our target equation is lambda m HAC will be equal to small lambda H plus small lambda m AC minus. This value can be written as Na plus Cl minus. Next can be written as and the last one now we have to arrange it such a way that we get this value. So to get this value we need to get this value this side. So H we need to get this side. So what we will do, we'll reverse this equation. Value of this much is equal to how much? 425.9. Siemens centimeter square per mole. Value of this much is 126.4 Siemens centimeter square per mole. And value of this much is 91.0 centimeter square per mole. So you have to arrange these three equations in such a way that we get these equations, and if we get these equations then sum of these will give the value of this. So we can keep it as it is. What we need to do is we need to subtract Na and Na. So we can AC has to remain this side, Cl has to go that side. So we can add this equation. Let this be equation 1 or equation 2 as per series. Equation 1 and equation 3. Let this be equation 1, equation 2 and equation 3. So we'll see this much now. In this equation we don't require Na anywhere. In this equation we don't require Cl anywhere. So we can subtract this, and if we subtract this from these two, then this Na will cancel this and this Cl will cancel this, and we will be remained with this much. So we can add these two equations and we can subtract these two equations. From these two we can subtract this one. So if we subtract this one, so this will be minus, this will become minus, this will remain plus, this will remain plus, this will remain plus, this will remain plus. So adding equation 2 and 3 and subtracting equation 1, we get this and this will be cancelled, this and this will be cancelled. So we'll get these two value, lambda H, lambda naught H plus lambda naught AC will be equal to addition of these two, 425 plus 91, 425.9 plus 91 minus 126.4 Siemens centimeter square per mole. So this value will come out to be 390.5 Siemens centimeter square per mole. Tips: do not forget to write units. Units carry half marks. So if you don't write units, only for value you will get half marks. So this was how many marks question? This was 2 marks question. Half mark for each step. So 1.5 and half mark for this. So 2 marks question. It was a 2 mark question. Now we'll see application of Kohlrausch's law. First we had seen it helps us to find the molar conductivity of electrolyte if individual molar conductivity of ions are known and vice versa. This we have seen in the previous numericals which we had solved. Second is it helps us to find the equilibrium constant and degree of dissociation of weak electrolyte. Say this we have seen in form of numerical. This we will see in another form of numerical. Before that, the theory part of that, let me make it clear. Unlike KCl or HCl or NaCl, when CH3COH is put in water, it does not dissociate completely. So it forms CH3COO minus aqueous and H plus aqueous. So when its concentration was unity, that means 1 portion by 1 portion and no portion of water was added. So this was 0 and this was 0. Say the fraction which when dissociates from acetic acid to form acetate ion and H plus ion be equal to alpha. That means the degree of dissociation be equal to alpha. Then at dilution, when dilution will take place, from 1 alpha will come out and this will form alpha and this will form alpha. So there is a relation between the degree of dissociation and molar conductivity at infinite dilution. At this molar conductivity of infinite dilution, if we keep in denominator, and molar conductivity of that at any given concentration will be equal to alpha. This is one value. and this we can relate with the value as lambda m will be equal to lambda m for say A and lambda m for say B for any electrolyte AB. Considering that A and B is 1:1 molar. Now we know that equilibrium constant Kc is given by, at concentration C, this will be C, this will be C, and this will be C. So equilibrium constant will become C alpha into C alpha divided by C into 1 minus alpha. So this will be equal to Kc equal to C alpha square by C square alpha square minus C into 1 minus alpha. This will be nullified and this will form alpha square 1 minus alpha. So instead of alpha we can put Kc is equal to lambda at any concentration m divided by lambda at infinite dilution square of this divided by 1 minus lambda at any concentration C m by lambda at infinite dilution. This is another application of Kohlrausch's law to find out the molar conductivity and equilibrium constant and degree of dissociation. So another is, it helps us to find out degree of dissociation and equilibrium constant. So these are the two applications of Kohlrausch's law. Based on the first application we have done the numericals. Based on this we will do one numerical now. Refer to page number 84 NCERT. It is said that the conductivity of acetic acid at a given concentration is 0.001028 mole per liter. At this the molar conductivity is equal to 4.95 10 to the power minus 5 Siemens per centimeter. So we have to find out its dissociation constant. Since it is an acid, so its equilibrium constant will be nothing but dissociation constant Ka. Acid dissociation constant we have to find out. So given value is lambda m at infinite dilution is equal to 390.5 Siemens centimeter square per mole. So this value is not in terms of per mole. That means this is not molar conductivity, this is simply conductivity. So molar conductivity we can find out from this. So this molar conductivity will be equal to this value 4.95 10 to the power minus 4 divided by concentration. This is the concentration, and as we had done earlier, since the concentration is in mole per liter, so you have to multiply it by 1000 to get completely it in centimeter term. So we'll just put the value now. So 4.95 10 to the power minus 5 divided by 0.001028 into 1000. This will become Siemens centimeter square per mole. Now lambda at a given concentration is found out, so we know alpha is equal to lambda at a given concentration divided by lambda m at infinite dilution will be equal to this value. Whatever value we will get, this will come out to be 48.15 Siemens centimeter square per mole. So we'll put 48.15 Siemens centimeter square per mole divided by this given value 390.5 Siemens centimeter square per mole. Fraction does not have a unit, so same unit will be nullified, and this value will be equal to 0.1233. Value of K, as we had seen earlier, was C alpha square by 1 minus alpha. So this will become value of C 0.001028 mole per liter, square of this value and 1 minus 0.12333. This can be neglected, and we can do rough approximation of this so that quickly we can get the value. So equilibrium constant K will be equal to, if we calculate this, will be 1.78 10 to the power 5 mole per liter. So this was the second application of Kohlrausch's law.